Today we shall discuss uncertainty principle and its application. Uncertainty principle tells that it is impossible to measure accurately and simultaneously two canonical conjugate variables like position or momentum simultaneously and accurately, and the product of their uncertainties greater or equals to h cross. In mathematical form, delta x delta p that is greater or equals to h cross, in or some books that is h cross by 2. H cross have a small value and h cross by 2 also gets a small value, so it doesn't matter, you don't have bother about it, you just emphasize on this thing. Heisenberg emphasized on two things, that is number one is in his statement simultaneously, and the second thing is accurately. Simultaneously and accurately. So one can easily ask the question why it is impossible to measure simultaneously or accurately the position of a given body or given particle. The answer is very easy. In classical mechanics, in previous year we know about classical mechanics. In classical mechanics, we can easily say that if we consider a ball of finite size, this is a ball of finite size, we know after some time or after some distance we can locate the exact position of the ball. We can tell that the ball in this position, the ball in this position, or in this position. Because this is a finite size, light get scattered through the ball and reflected on our eyes, we can see the image of the ball and we can easily tell the ball in this position. And if we know the velocity of the ball, then we can all easily tell the momentum of the ball. We can also tell the force acting on it. So in classical mechanics, we can tell the exact position, exact momentum, exact velocity, exact force acting on it. That is the exact value of those properties. But this is applicable only for macroscopic particle. But if we go to the quantum world, that is microscopic particle, then in quantum mechanics we already know about wave particle duality. Wave particle duality is nothing but in particle behaves like a wave and a wave also behaves like a particle. It is behave like a wave and particle duality. A particle behave like a wave and wave behave like a particle. That is electron. Example, electron behave like wave and particle also. So when electron behaves like a wave, so electron can have a wave function, that is we consider that is psi xt. Any wave function can have a function of space and time, since time is always changes, so the wave will proceed in this manner. So we cannot tell the exact position, the electron in this position, in this position, in this position, in this position. We can only say the electron in between in this region. That is the uncertainty in position delta x. We can only tell that electron in this between in this region, that is delta x. We cannot have exact position of the electron. If we don't understand it, consider your position. If you live in India, this is India, this is West Bengal, this is Kolkata. If we ask you, if we tell you that you live in Kolkata, then one can go from, if we tell you that you live in India, then it is find very difficult, because India is a big country. There will be many states, there will be many cities, so it is quite impossible to find you in India. But if we tell you that also that in India, in West Bengal, then it is quite easier than previous, that India, you will be more localized. Localized is nothing but your locality area. Localized means decreases your locality area. If we tell that India, it is quite impossible to find it out, but if we tell you that in India, in West Bengal, then it is quite easy. And then if we also tell you that in West Bengal, in Kolkata, then it is quite easier. So if we localize your locality, then it is quite easy to find it out. Simply, if we localize the wave particle, in this manner, then it is quite easier. Then the uncertainty in position decreases, because this region is small. If we further localized, this uncertainty is small, but from the uncertainty relation we know that delta x delta p, that is greater or equals to h cross. So delta p greater or equals to h cross by delta x. If delta x, uncertainty in position, decreases means we localize the wave in space. Locality, we localize the wave in space, then the uncertainty in momentum will increases. So the first statement, simultaneously, this is correct, because if we measure the position first, then we localize the wave function, and if we localize the wave function, then the uncertainty in momentum increases. So it is impossible to measure simultaneously. Why accurately? And if we can have also a wave function like this. We can have all this wave function like this. Sorry. So one can tell what is the position uncertainty. Position uncertainty is very small, because in this region the particle can be found out. In this region the particle can be found out. But what is the uncertainty in momentum? Uncertainty in momentum, here we can see that we cannot see the wavelength. When the wave is like that, we can tell that this is lambda, then can have a value, then we can find it out, p is h by lambda from this relation. But here we cannot tell that whether this is the wavelength or this is the wavelength. So the momentum is totally momentum. We cannot have the uncertainty in momentum increases if we consider a rest particle, that is psi xt 0, then we can say that the particle in exact in this position. Then from the uncertainty relation, delta x delta p, that is h cross. So delta p h cross by delta x 0, because we consider a rest particle, that is the wave function wave function 0, so that is it tends to infinity, so it's undetermined by undefined. So this is the uncertainty principle. This is the uncertainty principle. So it is impossible to measure accurately and simultaneously two chemical conjugate variable, example momentum, position, energy, time, etc. So from this demonstration we can say that if our wave function in classical mechanics, a particle is localized in space, so we can say the exact position, exact momentum or exact velocity of the particle or the given body. But in quantum mechanics, the wave function cannot be localized in space, and that's why we cannot tell the exact position, exact momentum, exact velocity of the given particle. This is the difference between the classical mechanics and quantum mechanics. If we localize the wave, then the uncertainty in position decreases, but the uncertainty in momentum increases. That's why we cannot measure it simultaneously. And why accurately? Because in the wave function cannot be localized in space. That's why we can have a value between the space. We can have a value because the wave function cannot be localized in space. Then the uncertainty, we can have this value, we can have a value range, from a range, a region. We cannot have an exact value. That's why Heisenberg uncertainty principle works everywhere. This we only tell about the uncertainty relation momentum, that is delta x delta p, that is h cross. There is also uncertainty relation is like this, delta e delta t, that is h cross, delta theta phi delta l, that is h cross. There are several uncertainty relation,